All right. It's my pleasure to introduce the chair of the next panel for the Lessons Learned panel, and that is Mr. Ralph Rowe. He's the director of NASA Engineering and Safety Center, NESC, at Langley Research Center. Ralph helped start the NESC after the Columbia incident in 2003 and has held that position directing that organization since then. He started with NASA in 1983 at Kennedy Space Center in engineering and did a number of increasingly responsible jobs at Kennedy and then at Johnson Space Center, working on the Space Shuttle program as the Vehicle Engineering Office leader from 1999 to 2003. Ralph has a Master of Science in Engineering Management from the University of Central Florida, and he's a Gamecock. He graduated from the University of South Carolina at Columbia in mechanical engineering. And Ralph has 150 LinkedIn connections.
Thank you, Ginger. See, how are the mics working? Can you hear okay? First of all, we want to thank you for the privilege to come talk with you. I think this is our Lessons Learned panel. I think you guys have already learned the most important lesson as I heard your introductions. A lot of folks talked about having a passion for spaceflight. And you're looking at a panel that's got a tremendous passion for human spaceflight in particular. And as I looked at everybody's resume, I think we have over 150 years of combined experience on this panel for human spaceflight. Most of that is with Bob Lang, but some of us younger folks are coming fast behind him. So the way I'd like this to work is we each have a short presentation to give you, and then what would be great is if you had questions or interaction at the end of those presentations. So first of all, I'd like to introduce the rest of the panel, and then I'll have some opening discussions, and we'll go right down the line and get to your questions, which I think would be the most important part and best for us. So next to me is Dr. Jan Davis. Jan is the Vice President and Deputy General Manager of Jacobs Engineering at the Marshall Space Flight Center in Huntsville. Jan began her career with NASA at Marshall in 1979 as an aerospace engineer, and she'd worked on the Hubble telescope and the Chandra X-ray Observatory. She also became the lead for the redesign of the Shuttle solid rocket booster external tank attach ring. In 1987, Jan joined the astronaut corps at the Johnson Space Center and has spent over 670 hours in space as a mission specialist on 3 shuttle flights, STS-47, STS-60, STS-85. And she's been around the Earth 325 times on those missions. After that, in '98, she was director of the Human Exploration and Development of Space Independent Assurance Office at headquarters. And then she returned to the Marshall Space Flight Center, where she was the director of the Flight Projects Directorate. And let's see, she was also served as the director of Safety and Mission Assurance at Marshall, and helped lead us to a successful return to flight in 2005. She did her graduate research work in mechanical engineering at the University of Alabama in Huntsville, but she also has degrees from Georgia Tech and Auburn in biomedical engineering and mechanical engineering. So I'm sure she's glad to be back at Georgia Tech. And Jan is in the Alabama Aviation Hall of Fame and the Alabama Engineering Hall of Fame. So Jan, welcome.
Thank you, Ralph. It's my pleasure to be here back at Georgia Tech.
We're gonna introduce everybody.
Everybody.
Everybody get this right. We're going to introduce everybody, and then we're going to go down the line.
Sorry about that.
Next to Jan is Jim Owen. Jim is the chief engineer of the Space Shuttle propulsion at NASA Marshall Space Flight Center in Huntsville. He was appointed to that position in 2006, and he is responsible for assuring the technical excellence of all the propulsion elements on the Space Shuttle, which is a very important job. Jim began his career in 1973 with NASA as a co-op student working in the thermal engineering branch at Marshall Center's Structure and Propulsion Laboratory. He worked his way up through that branch chief and division chief, and following assignment at NASA headquarters, he served in various management roles on the Space Transportation Directorate, including manager of the Next Generation Launch Technology Project Office. Jim is a native of Dallas, Texas, grew up in Huntsville during the Apollo era, and he earned his bachelor's degree at the University of Alabama in Huntsville. So welcome to Jim. Next to Jim is John McMahan. John is currently the chief engineer for the Space Shuttle program. John graduated from the University of Colorado in 1985 with a bachelor's degree in aerospace engineering, and in '86 with a master's degree in aerospace engineering. He worked at various positions at the Johnson Space Center in the mechanical design and analysis branch, and performed design and analysis of a number of pieces of hardware, including the Shuttle pole crew escape system and flight and test support equipment for the Shuttle and Space Station Freedom docking systems. And he was also the subsystem manager for the orbiter docking system. He was selected as the chief engineer of mechanical systems also, and in 2000 he was selected as the engineering directorate's chief engineer of the International Space Station. So John's worked both the Space Shuttle program and the Space Station program. He was an inaugural member of the NASA Engineering and Safety Center when we formed it back in 2003, and was our Mechanical Systems Technical Fellow. And John has received a number of awards throughout his career with NASA. Welcome, John. Next to John is Bob Lang. Bob's had a distinguished career in NASA for 29 years. He is currently the United Space Alliance Chief Engineer for the Shuttle program. And in NASA, he served as the Apollo Lunar Module and Skylab, on the Apollo Lunar Module and Skylab workshop prior to the Shuttle program. And his last two assignments in NASA at the Kennedy Space Center was the Kennedy Space Center Director of Safety and the Director of Shuttle Engineering. After he retired in '96, he joined the United Space Alliance and is, as I said, the Vice President and Space Shuttle Chief Engineer. Welcome, Bob. And last but not least is Steve Sullivan. Steve is the Launch Vehicle Processing Chief Engineer at the Kennedy Space Center. Mr. Sullivan is responsible for all engineering aspects related to integration and processing of flight hardware and ground support equipment at the Kennedy Space Center. All the pieces come together at KSC, and Steve is responsible for that. Steve has a BS in electrical engineering from Auburn University. So those are our introductions, and we'll go one by one, and I'll start off with a few comments myself. No charge from me. My organization has prided itself in trying to return to writing engineering reports. So we try to stay away from PowerPoint as much as possible. So I hope all of you are honing your skills on writing engineering reports and papers. I was a part of, in the last decade, I was a part of two studies that I think are rather significant. I think Ginger mentioned privatization. In 2001, the Space Shuttle program did a study on what it would take to privatize the Space Shuttle. And right about now, with one flight left to go, I really wish we'd have done it in 2001. But when we did that, we wanted to take a look at what were the specific elements of the Space Shuttle program that made it successful and safe. And we wanted to capture those elements and then see how they could be implemented in a private company. So we did a very thorough study at looking at all the elements of the Space Shuttle program that made it successful and safe. And then again, unfortunately, after Columbia, we did a similar study. We wanted to look at what aspects of the shuttle program and previous programs helped make those programs successful when they were successful. And we wanted to make sure that we were implementing those upon return to flight. And I know a lot of you would be most interested in lessons learned that are related to hardware components or technical analysis. But what I'll tell you is the most important lessons that I've learned in 29 years with this shuttle program are not related to the technical hardware. And I think as each of our folks talk, you'll hear some common themes, and it's about building relationships and trust and communication and skills other than doing technical analysis and design that you need to make sure you're working on throughout your career. And what we learned on those two studies in the past decade was that we had inherited a safety philosophy from the Apollo program that we've utilized in the Space Shuttle program throughout its history. And that safety philosophy has three important tenets. And those tenets are strong inline checks and balances, and I'll talk about each of these so you know what I'm saying with the terminology. Strong inline checks and balances, healthy tension between the responsible organizations, and value-added independent assessment. Strong inline checks and balances are things that I think you guys probably use as common sense in your own work as you're working on a dissertation or a difficult problem. You usually, I'm sure, seek out your most knowledgeable peer who can critique your work and help you understand where you might be weak or not made the strongest points before you go to your professor or your advisor. And that's really what strong inline checks and balances are. It's engineers checking other engineers. It's even the world's best engineer is going to have a bad day. And in our business, in human spaceflight in particular, you have to do everything you possibly can to prevent mistakes. And so that's why it's so critical that engineers take the time to review each other's work before we commit to whatever decision we need to make. And so strong inline checks and balances are a foundation to our success and safety in the Space Shuttle program. That's at an individual level. At an organizational level, so we want to have similar checks and balances, and that's what we call healthy tension between our responsible organizations. And healthy tension is the elements of your program or organization, any high-risk, high-benefit program, project, organization needs to have healthy tension between their responsible groups. And that's represented as an example if you have a program manager, a chief engineer, and a chief safety and mission assurance officer that has a safety organization and an engineering organization and a programmatic organization. You have to create healthy tension between those three organizations in order to make good, well-informed, balanced decisions. The program manager, who may be the decision maker, needs to hear the different perspectives of each of those organizations, from the engineering team, from the safety team, from the program team. And only if those folks are on equal footing within the organization, represent separate but equal chains of command, and have the resources and the skills to properly present their organization's perspective. And they fulfill that role so that the program manager then can make a well-informed decision after hearing each of those different perspectives. That creates, in our mind, a healthy tension within the organization. Healthy is key also because when that gets out of balance, when one organization is too strong or one organization is too weak, in the case of in Columbia, you might remember the Columbia Accident Investigation Board felt that our shuttle safety program at the time was too weak and didn't have the resources, funding, technical skills to really provide the shuttle program and the program manager a different perspective on foam loss or any other very difficult technical issue. So creating that environment where you have separate but equal chains of command that can offer different perspectives and create that healthy tension, allow a program manager or the head of an organization to make sound decisions after being informed by each of those perspectives is healthy tension. Then the third and final piece of our studies was value-added independent assessment. Maybe some of you have experienced this in your own work. Often when you're working long hours on a particular problem and you've spent days, weeks, maybe months in some cases on a problem, and you're just not getting there. You're not seeing the light at the end of the tunnel. And then say maybe a professor or a peer will come in with a fresh set of eyes and see right away what you've missed because you've been working so hard at it for so long. And value-added independent assessment is fundamentally just that. It's that you take the time to bring in outside experts to look at a problem that you may have been working on for months, you may have been flying with for years, and bring in a fresh perspective on those problems. And sometimes it's difficult to stop, bring in an outside team. You often think, well, that's just going to slow us down and we're not going to get there. But in the end, when you do take the time to do that, you end up with a different perspective on the problem and often a more robust solution to the problem. So those three elements, nothing to do with components or technical analysis, are, in my opinion, the secret formula to success in human spaceflight. Strong inline checks and balances, healthy tension between your responsible organizations, and value-added independent assessment. And then on top of all that, if you do those three things right, you have to spend as much time as you do on solving technical problems on creating the right environment for those processes to work. And that's the personal relationship side of being part of a team, being part of an organization, building trust within that team, because you want to create an open environment where you can have vigorous technical debate on different sides of an issue so that all sides are heard, no one is inhibited, no one is afraid to talk about their perspective or someone else's perspective. And that really takes a great deal of time building strong personal relationships within your team. All of us as engineers, we want to spend all of our time on the technical aspects of the problem. But you have to spend just as much time on the personal relationships and the teamwork as you do on the technical side. If you have the right solution and you're not able to communicate it with trust and respect to your partner, we don't get to the right solution as a team. So the personal relationship side is just as important as the technical aspects. So to me, you combine all four of those things, and that will lead you to success in any, not just human spaceflight, any high-risk, high-benefit endeavor. Thanks. Jan?
Sorry about that. Thank you, Ralph, and it's great to be back at Georgia Tech. Just to give you a sense of when I was here when John Young landed on the moon, and we all at Georgia Tech were very proud of that, and he also carried a "To Hell with Georgia" flag and put it on the moon buggy. So that was really a neat time for me here at Georgia Tech. Always, growing up in Huntsville, Alabama, always been interested in the space program. But I was thrust into both returns to flight for the shuttle accidents. The first one, after that accident, we were changing a lot of the space shuttle, and in particular the boosters, and I was in charge of redesign of part of the booster. So I went through all the reviews and independent groups who were looking at how we were getting back return to flight. And then after Columbia, I had been working space station before that, and space station hardware, flying hardware on the shuttle. And after the Columbia accident, I was named head of safety for Marshall, which was responsible for the external tank. So it was not only building back the safety organization, but also certifying that the tank was safe to fly. So I've taken some of those experiences and put them together to hopefully communicate some of the things that we learned from those, as well as some of my other experiences with NASA and human spaceflight. But also I want to share with you some common themes that we found from other incidents at NASA that were non-human spaceflight. There was a report done back in the early 2000s about the failure of the Mars Climate Observer it failed to reach its orbit. And so they did that mishap study, and they were asked to look at lessons learned across all NASA incidents and accidents. And there was a great report that came out as a result of that. And there were some common themes for all of those incidents and accidents. And it's very interesting that if you look at the top common themes, you see a lot of what Ralph talked about, communication and reviews and those kinds of things. And so I'm going to talk about the top, well, communication is not the top three, but I'm going to talk about two of the top three, and then also communication, and you'll hear some other folks talk about risk management. So these are from 8 reports consolidated, and these are the common themes from those 8 reports. So the 3 that I'm going to focus on are first communication, then decision making and reviews, and listening to the hardware. And some of this you've heard in other discussions yesterday, and some of the same phrases like listen to the hardware. I promise you I didn't see their slides, and I didn't make mine up last night. It's just that these things are inherent in our business and things that we have to do. So we'll move on to the first one, which is communication. And that's key to everything that we do for a successful flight or successful program. First of all, you have to develop a culture where everyone's opinion is heard at all levels. And as Ralph said, you do that by building a team and understanding everybody on your team has value and has an opinion. And so you have to seek out those fresh look ideas from other people. In Challenger, there were some situations where some information was not communicated at all levels, and so the people at the top didn't have the same information as the people at the bottom. And so you have to value everyone's opinion, and if it's important enough to be elevated, you need to elevate it and make sure that those opinions are heard. The second one is encourage dissenting opinions. Brian O'Connor, who you heard yesterday, has a great talk just on that topic about the doubting Thomas, where that term came from, and people who challenge you. John Young, another Georgia Tech graduate, was great at that. He was not afraid to, in a meeting of 300 people, to stand up and say, well, how come it's this way? He says, I'm just asking. That was his famous line, I'm just asking. And he was just one of the brightest people I've ever met. And he always made a good point. It made you just go, And so you need that kind of person to be up there and just ask those kinds of questions. And so good managers, I think, will find somebody who they know they can trust with giving them an honest answer. And they say, well, what do you think about that? So the other side of that is if you are on the other side, you're not asking for dissenting opinions, but you don't agree with what's being said, you need to speak up. You can't just sit quietly in a meeting and then when you get home, send off an email saying, can you believe they did that? I don't think that's a good idea. You need to say that in a meeting. So not only ask for that dissenting opinion, but if you're not in agreement, and that's hard sometimes to say that, if you don't agree with what's being said. But that's very important. Communicate, communicate, communicate. I think that was on Brian's chart yesterday. I mentioned the MCO, Mars Climate Observer failure. The failure was caused by different teams had different ways of doing their navigation, guidance, whatever. And one team used English units and one team used metric units. And so the team that got the vehicle to Mars had one system, and the team that orbited Mars had another system. So when it went to orbit, the GNC, the guidance, navigation, control, didn't work. And they found the root cause of that was because these teams weren't communicating. And you think, well, that's easy. I'll just talk to people. Well, you know, email is not communication, and texting and all that stuff we do now. You got to go talk to people and build this team and really understand what the other teams are doing. Engineering is all about teamwork. I'm sure all you students are part of teams. When I was a freshman at Georgia Tech, we had a design team, our freshmen. And on our team was a marketing major, and we're like, what's a marketing major doing here? And it's because, you know, they're all valuable. You got to communicate, and you got to be able to communicate what you're doing to the rest of the world. As Ralph talked about, develop independent lines of communication, either with independent teams with the same goal or independent technical authority. This was something that was very important after Columbia that we set up, and his organization, the Engineering Safety Center, is vital to that. And you heard about that from Brian yesterday about how we didn't have the good, healthy tension, that some teams were sort of making the decisions and some of the other teams were quiet about it. And so we need that healthy tension. We need independent lines of communication so that you have independent opinions is very important. The next are decision-making and reviews. While processes are good and necessary, don't let them replace good engineering judgment. Typically, if you are in industry and there's an accident, you know, somebody falls off the roof or something like that, the first reaction is, oh, we need better procedures and we need better processes, and they just change everything and make you have more regulations, which is, it's necessary that you have those. And it's the same thing in engineering. You know, it's necessary you have those processes and those checklists and those procedures and those quality stamps, but don't let them override, you know, good common sense engineering. You know, just say, well, why are they doing it that way? You know, why this doesn't make sense. You know, think about that. Don't just blindly follow these processes and procedures, although they are necessary. You have to use that engineering judgment. That's what you're in school for, is that good engineering, seat of the pants, as we call it, engineering. Beware of data and statistics to explain away a problem. Explain data well in briefings. You heard that yesterday, I believe, from Bob. He said that, you know, beginning Shuttle days, people were interpreting data in different ways, and you can slice and dice it any way you want to. You know, that's the great thing about data and statistics, but you have to be careful with that you slice and dice it the correct way. Before Challenger, there were some data, as Chris Singer talked about yesterday, that were interpreted differently by the contractor and versus NASA, and some people had some data that was not available to the other group, and so, you know, you have to be careful how you treat data and how you treat these big computer models. You know, make sure, again, using your engineering judgment, that they make sense. When we were getting ready for return to flight after Columbia, we had a new administrator, Mike Griffin, who's, again, a very bright man. And some of these people on this panel, I think, were in the room when he came in one of our reviews and sat in the back. He didn't want to sit at the front of the table. He just wanted to sit in the back and listen. And we were talking about characteristics of foam and probability of foam falling off and debris and all that. And he just stomped up to the front of the room, got something to write on the blackboard with, and said, you can't explain it that way. The data you're using and the way you're explaining it is not the way we need to explain it. And he said, this is the way you need to explain it. This is what probability is about. And we're all just kind of looking like, oh, man, we've been working on this for like, you know, several months. I can't believe we're going to have to redo it. But he was right. You know, we needed to look at it a different way, in a way that standard probability statistics used. And it delayed us a couple months, but it's just something that you have to be careful how you treat data. Be on the lookout for groupthink in meetings and discussions. When I was head of safety at Marshall, we did shuttle return to flight, but we had other programs going as well. One was Gravity Probe B, which was going to prove some of Einstein's theories of relativity, and that's about all I know about it. But anyway, this program had been going on for a long time, and we were at the pre-ship review. And there was a a black box, an avionics box that had failed the thermal vacuum test, and they had to change some wiring, and we're getting ready to ship it again. So we're going around the room, started with the chair of the board, and he said, you know, I think we're ready to go, we're ready to ship, and once we ship it to Vandenberg, we'll launch it. So when you pass the pre-ship review, chances are you were going to launch whatever that configuration was. Went around the table, everybody agreed, yep, we're ready to go, let's ship it. And got to me, and I said, well, how come we're not going to put it back through thermal vacuum test after we changed the wiring, changed the configuration? This program was 40 years old. I mean, it was a long program, and it was finally going to fly. And I said, we've waited 40 years for this. It's going to take another month, a slip in schedule, to test it in thermal vac to make sure the box works. But I think that's what we need to do. And then everybody was like, yeah, I guess we should. You know, it's just kind of this groupthink mentality, and you can get caught up in it really easily. And so just be careful of that and make sure that you don't get caught up in that. It's an easy thing to get caught up into. Conduct thorough reviews at the right phase and at the right level. It's important to review your progress with the right people there and make sure that you have adequate reviews. And I think Shuttle has done a great job with this after the program has evolved. It's a very thorough review at all levels, and that's just another thing to make sure that you do. Listen to the hardware. You heard Chris Singer say this on his chart. It's listen to the hardware. Well, how do you do that? You don't rely on past performance and analysis only. Test and evaluate where possible. We've talked about the flight rationale that we lost on Columbia and Challenger. Brian talked about it yesterday, and Ralph mentioned it also, where we saw the hardware telling us something. You know, in Challenger, the joint was rotating more than we had initially predicted. And for external tank and shuttle before Columbia, foam was coming off in a different way than we had before. But it didn't cause a problem, so we thought it was okay. And I was in those flight readiness reviews too, and it made sense to me. And so, just because it worked before, it doesn't mean necessarily that it is a good measure of that it's going to work again. You really have to analyze it. You have to test where you can. You heard about that yesterday also. Test as much as you can and evaluate. It's kind of like when you run a yellow light when you're driving. Everybody's done that, and you go, well, I didn't get a ticket. So next time it's about to turn red, but I'm going to run it again, and I'm not going to get a ticket. And then finally, you'll get a ticket. It's just that because it worked before, you think, well, I'm going to do that again. And so you just have to be careful and watch that. Second, understand the operational constraints of the hardware and what that data were based on. Again, before Challenger, we had some discussions about the temperature that the hardware was qualified to. There was some people had different data than others, and so we weren't really sure what those operational constraints were. As I understand it, I wasn't part of the program then, not until after Challenger. But you have to know what those constraints are. The Challenger, in my opinion, was not a bad design. But the second bullet says operate in the environment to which the hardware has been tested and qualified. You have to understand those limitations of what it was tested and qualified to. But the joint was operating outside of what it was qualified for and designed to. And so that, in addition to the hardware telling us something that was different than what we had expected, led to the accident. So make sure that you understand its limitations. Fly what you test and test what you fly. That's another mantra of our business, where, and you heard that yesterday also. We had some failures on Apollo 6 where we had some ground testing with some braided fuel lines, and because they were not at vacuum, they behaved differently, and the air, saturation of air around those fuel lines was different when it went to altitude, and the fuel lines broke. And so if you're going to operate in that environment, you need to test in that environment in a vacuum. And so it's very important that once you do test it in that configuration, don't change something else, because that may have an unintended consequence that you didn't test for and that you changed when you changed the configuration. So that's the summary of the 3 points: communication, decision-making and reviews, listen to the hardware. The fourth one, it's in the top 4, risk management, I think some other folks are going to talk about. I just want to close by saying that the Shuttle, working on the Shuttle program for the last 30 years has just been a fantastic program. You've seen the accomplishments, and I've been fortunate enough to work on the engineering side, the safety side, flying the Shuttle, the management side, and I feel very blessed. And I hope that some of the things that we're sharing with you today, you will carry forward. It's exciting to hear what your plans are, and that you will carry these lessons that we have experienced and hopefully learned into the programs that you work on. And so now it's up to you. Thanks.
All right, thanks, Jan. Jim?
Thank you, Ralph. Thank you, Jan. It's been just a treat for us, all of us, to be here this week with you students.
We'll try this one.
How about now? Okay, it's been a treat. This week has been a treat for us. Get to be around youngsters and students. It's been refreshing, and it's fun to see your enthusiasm. What I'd like to talk to you about is how we're ending the Shuttle program, because we're finishing quite strong. We've done a number of things in the last 21 flights, and we'll end with 135. It'll be the 22nd flight since STS-107, and the accomplishments have been significant. We've completed the International Space Station. You've heard about that. I don't know that we really focused on it, but we flew a mission to Hubble and did a servicing mission at Hubble, which was an enormous challenge, and it refurbished that science instrument such that it can operate for a number of years into our future, and it's been an outstanding science observatory. But along with those very public accomplishments, we've also accomplished a lot on the vehicle. We've implemented significant corrective actions. And all of these lessons learned and lessons learned databases that you'll hear about and maybe see, they're only learned if you've taken action to correct a problem. And action comes in different forms. It can be a design change. It can be adding a new requirement, improving a process. It can be adding an inspection step. But if you don't do that, if you don't follow through with corrective action, then these lessons are just experiences. I heard Brian yesterday talk about proactive risk management. That's what we've implemented in the last few years on Shuttle, and we've done it quite well. The program has done it quite well. What that has involved is a couple of things: solving problems, nagging problems that we've had for years that we've solved, and the other one, the major one that we've worked on, is the ascent debris risk. We've greatly reduced the ascent debris risk. And I'm going to give you a couple of examples of problems and debris risk. We have these things we call engine cutoff sensors, ECO sensors. Got to use an acronym. And what they're intended to do is sense fuel depletion. And the reason you want to do that is because if you starve the engines, you'll unload the pumps, overspeed the turbines, the turbine will destroy itself and you'll have a catastrophic failure. So we think they're very important. And on the hydrogen side, we began to have intermittent failures. So you've had, in your car, you've had intermittent electrical problems. You couldn't trace it down. Well, this one is pretty subtle as well. There are four of these circuits and we required 2 at end of flight to protect the engines. And what we began experiencing is we load the tank, and we check these circuits periodically while we load the tank. And sometimes they'd work, and sometimes they wouldn't work. And if they weren't working, we'd scrub, and we'd scratch our heads and think about it. We'd drain the tank, and we'd go out and check the hardware, and they'd be working. Every time, without fail. So, and it was kind of a comedy of errors. We'd send our program manager, Wayne Hale, a fine gentleman, out to the press, and he'd have about as much information as I just relayed to you. He said, sometimes they work, sometimes they don't. Well, we don't know why. I mean, sometimes we'd come back the next day, load the tank, everything would work, and we'd fly. So we checked out everything we could think of. We checked the sensors, wiring, the electronics boxes. This stuff crosses several of the elements. So everybody did the best job they could to try to figure it out. And what we worked on first were the sensors themselves. We modified the manufacturing process and tightened up some tolerances. And we thought, well, you know, we can't duplicate this in test, but maybe that's it. Maybe just making the sensors better will work. Then on STS-122, we had a reoccurrence of the problem. Right around Christmas, 2007, we at NASA seem to have problems at Christmas every year. And it just ruins the holiday time. But we worked through Christmas trying to figure this one out. This time when it failed, we had several circuits fail almost simultaneously. And because of the previous work we'd done, we had a little bit better information on when they failed. And what we found was they seemed to be failing when the cryogenic propellant, the liquid hydrogen, very cold, minus 423 degrees Fahrenheit, would pass this feed-through connector, part of the tank wall. It passed the circuitry from the sensors in the tank to the avionics box on the orbiter. So we figured, hey, this is thermally induced. We got to figure out what's going on with that connector. And what we found out through testing on the vehicle at the system level and off the vehicle at the component level was we were breaking the pin-to-socket interface at this electrical connector, causing an open. And what it turned out to be was, as it got cold, as that connector got cold, the pins were getting cold enough to condense and freeze air on the pins. And that wasn't the problem. That wasn't the whole problem. As the rest of the system chilled, you get a lot of, everybody knows what alpha delta T is, coefficient of thermal expansion and change in temperature. This system would move just a little bit. And you'll see a lot of places on cryogenic systems where structures move because they shrink. And as that occurred, the sockets would ride up on the frozen air just enough to open the circuit. Well, that's pretty subtle, we thought. But it did explain that when you drain the tank and warmed everything up, the air melts and we're back to our closed circuit again. So once we got that kind of data, that kind of information, that kind of knowledge, the fix was pretty simple. We just soldered the sockets to the pins, did the way we did the wiring on the outside of the tank, and it's worked great. It's worked every time, so the mystery was solved. But the point is we didn't tolerate poor performance. We stopped. The program manager, all the managers said, hey, this problem has recurred. We're not going to live with it. We're going to go get the data we need. We're going to understand the problem. We're going to put in corrective action, and that's what we did. So that's what Brian was trying to tell you about proactive risk management, and that's what we have implemented. The other example I want to talk about is a design improvement we implemented on external tank to reduce ice formation on components we call brackets around that attach the LOX, liquid oxygen feed line, to the hydrogen tank. It's a great big 17-inch line, and it does exactly what it sounds like it does. It transports liquid oxygen from the top of the tank. The liquid oxygen tank is on top, to the engines at the bottom. And this 17-inch line has to run the length of the hydrogen tank. It has to attach to the hydrogen tank on the external part of the tank. These brackets were originally made of aluminum, and because of geometric constraints of trying to fit everything in there, we couldn't put enough insulation around the brackets to preclude ice formation around the entire bracket. So we'd always form ice. The program knew it from day one. And sometimes it would become a debris hazard. During ascent, the ice would break off, fall off, and potentially impact the orbiter and do tile damage. It was a complicated problem. We had conflicting requirements. We had to attach to a hydrogen tank, which again was at negative 423 degrees Fahrenheit. These brackets and the feed line have to do its structural and main propulsion system jobs. They have to structurally hold everything together, and they have to transport this liquid oxygen to the engines. They have to articulate, because I mentioned everything on this cryogenic system changes shape when you get it cold. It was in a spot on the system where we couldn't run power. We couldn't put heaters on this system. There's no practical way to get heaters to that area. And as I mentioned, our ability to insulate was limited. So the design modification that we chose was to do a material change. We chose titanium brackets. We redesigned the bracket system, and because of the fundamental lower thermal conductivity that the titanium has, we were able to eliminate a great deal of the ice formation on this bracket. Now, that's not classic engineering design. We didn't meet all requirements. We still formed some ice and some frost on that bracket. But it was an enormous risk reduction and a very effective way to implement risk reduction. It's flown 11 times, and it works like a charm. And it's been a significant addition to our continuous improvement, a culture of continuous improvement over the last few years. That's just one example of risk reduction that we've implemented over the past 21 flights. Been a number of other design changes that I won't go into. Also improved processing, improved manufacturing processes. But if we add all those things up together and based on just some simple kinetic energy calculations, we've implemented a 2 order of magnitude reduction in risk for the ascent debris. Now that's pretty significant given the constraints under which we worked, that I mentioned. We didn't want to make major block upgrades to the tank. We had to go pinpoint problems and try to implement specific design fixes where we found them. So what does 2 orders of magnitude mean to you? You know, if your probability of occurrence is 1 in 50, now you're at 1 in 5,000. Well, that's not an unusual risk posture to be in human spaceflight. It's a risky business. The other thing that went along with the risk reduction activities were improved situational awareness. We added a great deal of ascent imagery that we could look at the systems during flight, and we improved the way we image the tank post-orbiter separation. And we collect all that data, and and we also added the ability to do on-orbit inspection of the orbiter. You heard about that with the robotic systems yesterday. Now, all this collection of information and data and improved situational awareness has not given us a zero-risk posture. We still fly with risk. but it's very well understood, it's very well characterized, and we are able to make very good decisions. I call them informed decisions. And we do that during each mission. So when you students are working difficult problems in the future, I want you to ask yourself three things. I want you to say, do I understand this situation? Do I have adequate data? And can I make an informed decision? And I think if you just go through that kind of a simple thought process, it'll be wise. Now, yesterday I heard Brewster tell you he was lucky. Now, I think Brewster probably was well prepared for any opportunities that came his way in life. But what I want to tell you is we are all lucky. We were all lucky. We are all very privileged to have this opportunity to participate in a mission of exploration and discovery. For me, it's been a career of lifelong learning. It's been fun. When I retire, it's going to feel like a graduation event because I feel like I've learned every day along the way. So in closing my part, I just want to challenge you folks, you youngsters, to do a couple of things for me. First, try to become a little bit of a student of history. You don't have to dwell on it or focus on it or spend a heck of a lot of time on it, but try to learn from our experiences. Most of your wisdom is going to come from your own experiences. But human spaceflight and spaceflight in general is rich with opportunities for you to learn from the lessons that we are sharing with you, our experiences. And the second thing I want to do is kind of echo what Ralph and Jan talked about. I want you to develop your interpersonal skills. I want you to work on developing great communication skills. I think most of you already have good communication skills. But when you're working your problems, you're going to be in multidiscipline teams, and you're going to be a technical expert. And you're going to have to communicate what your area of expertise means to the broader team. And everybody's not going to understand. So you're going to have to find ways to bridge that gap of understanding and explain what they need, what everyone needs to understand about the problem. So I'm going to turn this over to John, but for each of you, I wish you missions of exploration and discovery, and I wish you lifelong learning. Thank you.
Thanks, Jim. We're on track. We're halfway through. We've used less than half the time, so let's see if the bottom part of the lineup can hold up to end.
I don't know about that. Is this one working? Can you hear me from here? Okay. Well, let's see. I'm John McMahan. You heard my introduction. Thanks for the nice introduction. And I, too, am very pleased to be here. It's just so exciting to just feel the enthusiasm within the whole group. And I know you guys are getting, I've talked to a lot of folks. I know you guys are getting a lot out of this. And I think it's really great for us to be able to share some things we've learned in our careers. I got a long way to go. I'm still not done yet. So we're finishing Shuttle, but there's a lot more out there for me as well. One of the things, I struggled with what do you write down for lessons learned. I've been just a little bit more of my background. I've started in the mechanical design, structural design area, actually hands-on stuff. Learned a lot of little lessons there, not so much in big teams, but then, as you evolve, you kind of get into bigger and bigger teams and you see some of these other kinds of not technical lessons learned, but more of the communication kinds of and teamwork types of communications, lessons learned. But to me, it's just amazing how much we continue to learn as we fly, continue to fly the orbiter or the shuttle over the 30 years. As I continued to grow and took on bigger responsibilities, the problems that we had, we were always able to find our ways through them. But we had failures that were big and failures that were small. But we learned from both the failures and the successes. And I think I have some discussions in here that are going to talk about some of the successes as well as the failures. I talk really more about kind of top level. These aren't the hardware design issues and things that we ran into along the way, but it's more kind of a general sense of what we learned and some of the key ones as I see them. It wasn't always easy. We lived through some very tough times. You saw it on the video this morning. And you heard it in discussions yesterday about the two big accidents. Those were obviously, incredible lessons learned there. We really had to step back and think through that. And so I say the team always made it look easy. Those were not easy times. But in general, I think NASA has such a passion for doing what we do, and I mean in the broader space community, that we really make it look easy. So these observations are, from me particularly, you're going to hear a lot of common themes. It's amazing how much, I guess, we do communicate, because I've got stuff in here that other folks seem to have in their charts, and a lot of the same themes we heard yesterday. I think we heard some really good lessons learned yesterday. But I think I've got some things that I learned as a space shuttle chief engineer post-Columbia. So I really didn't, grow up with the design and development of the vehicle, but I did earlier in my career have a responsibility for the subsystem management of the docking system, and that was an area where, if I look at all my jobs I had, that was where the rubber met the road. I mean, it was responsibility for a very key piece of hardware where I had a team I had to lead. We had tests we had to do, analysis we had to do, certification we had to do, and then we ended up going and flying it on STS-71 for the first shuttle Mir docking mission, and then 9 more subsequent missions to Mir, and then now we use it after a bunch more redesign on the International Space Station. And so learned a lot of stuff in that experience, as well as in the Space Station chief engineer job that I had, where I was, that was earlier in the development of that system, and that very complicated system. It's a huge integration, kind of a nightmare almost, getting this thing assembled on orbit. And so I learned a lot kind of from on the development side there, as well as how you then bring it to orbit and go through the operations piece. So the 4 things that I wanted, and I guess I didn't start moving my chart. That's what I just said. The 4 things I wanted to hit on that to me are, I mean, there's a million lessons learned out there, but these are, in my opinion, some of the really big ones that I guess where I'm at today with all my experiences I feel strongly about. And the first one is preserving design margins. The second one is having a demonstrated understanding of physics and using a well-balanced set of testing and analysis to get there. That's so important. Relentless curiosity and continuous improvement. You've heard a lot about that from all the different elements. So I'll go into that a little bit. And then just the utilization of a highly effective team and organization, kind of what we are. It's really kind of integrating everything we do, all the different disciplines, all the leadership aspect, the safety aspect, the communication aspect, and so I just have a couple of bullets on that. So preserving design margins, next chart. Okay. As I said, after flying for 30 years, it's amazing how much we continue to discover. After STS-1, of course I wasn't there, but it was a true flight test. We had astronauts on board, but it was truly a flight test. We had never gone through the flight regime. And so at that moment, we really realized our true environments. And I know the vehicle had some structural damage even on STS-1 that we had to deal with later. And even more recently, what MEI and IOP are main engine ignition and ignition overpressure environments. That's the big, huge kick you get when you start the main engines and then you start the solid rocket boosters, and you get this shock wave reflection in the vehicle. And back in STS-1, we had a problem with that, where we had some structural damage we had to deal with and had to make some modifications. And then even as late as just a year ago, in some work we were doing, we discovered that we were still not enveloping. Our certification didn't envelope the environments that we were actually producing with the vehicle. So we had to jump through a lot of hoops and scrub our analysis in quite a bit of detail right before mission to try to get some structural margins back in the box and show we were certified to fly. That's after we've been flying a mission and flying a vehicle for 30 years. It was pretty incredible. We often discover hardware features. We call them features. You get on orbit. My docking system was one example of that. We kept discovering features after we started flying it. We'd get on orbit and we'd try to use the thing in a certain way, and it wouldn't act exactly like we thought, like we'd tested, and didn't understand why, but we would eventually be able to understand the physics of it and why it didn't work that way. Analytical tools over the evolution, or in the 30 years, 25 years I've been here, they've evolved, they've become more sophisticated, and I think it leads us to being able to understand physics better, but it also helps us, or makes us, or identifies issues for us. That's how we ended up with the MEI and IOP environment update because of our more sophisticated analysis that got us there. We also have process creep, hardware obsolescence. All those things play into why we continue to learn. And so really the lesson learned here is, and you've heard this several times, we're never smart as we think we are. So we thought we understood it all, but we continue to learn as we go. I think the shuttle designers early in the program served us very well. I think they designed in margin, and so that's really the key of what this lesson learned is trying to maintain design margin. They were, with that, able to tolerate unforeseen failure modes. We go at great lengths to try. You heard about the fail-safe scenario or requirement used on systems, but sometimes our failure modes don't work exactly the way we thought in a structural sense. And in structure, we typically don't have redundancy, so you need to be robust in that, and margin can help you out there. Lower fidelity analytical tools in that time probably drove that more conservative approach because they didn't have the insight as much as they needed, so they would more conservatively drive that. And that's really the way I'm defining what margin is. It's really the capability above what is required. We have safety factor requirements that we are required to use, and we really guard those. The safety community, the engineering community really guard those well. Some of the healthy tension we were talking about, they challenge that at some times when you're in a bind, but the engineering community holds those very strong. But there are other things, uncertainty factors, conservative assumptions, engineering judgment plays into everything we do in modeling. And these are ways that we can bookkeep margin that helps us in the end or when we actually go fly missions. There's significant benefit to having margin in the system above just your safety factors. It protects against the unknown unknowns. You heard Brian talking about unknown unknowns yesterday. And so it helps you protect you there. The environmental uncertainties, things that you can't really represent in ground testing. We typically try to test as like we fly and fly like we test. In our ground testing, but you can't always get there exactly, so there's some uncertainty in that. And it provides a capability and a flexibility when we're on orbit or during ascent or anything to respond to the anomaly that you might be having. So my lesson learned or recommendation is that we incorporate margin in the design. There's really three parts of it. Really incorporate the margin in the design phase. Don't overdo it, obviously, because it doesn't come for free. Next chart. Sorry, I keep forgetting I'm the operator. It doesn't come for free. It does, add weight to systems. But again, I think there's a balance there that it does help provide something. I think also that there's a tendency with our more higher fidelity tools that we're using nowadays, a better understanding of the physics of what's going on, that there's a tendency we may be removing conservatism. So I think we just need to be careful about that. And the second part is really to understand how much margin you have in the system. I think this is so key. A lot of times we don't go to that extra step in a test or an analysis to really explore the envelope. We kind of take it to what's the requirement, and then we don't go beyond that. I think it's so important to go beyond that and understand, take your hardware in your testing phase to failure to understand what capability you got beyond that. And then implement a comprehensive flight instrumentation and validation of these environments. That's one of the things that sometimes is on the chopping block early in a program, but I think as engineers, and we really need to fight for that because we're going to need that data to help validate the models and the use of this hardware later. And the third thing is really to consciously preserve the margins. So once you understand them, of course, now they're on the table, everybody knows about them. The ops community will want to use some of that healthy tension again. The program and the ops community will want to utilize that just in a normal sense, but I think there's some value in keeping some of that on the other side so that it's there for a rainy day or a bad day, I'll say. Then in an off-nominal situation, you can go ahead and do a risk trade and understand what you're trading if you decide to trade some of that margin for compensate for a degraded system or some mission performance. And the mission phase you're in may dictate exactly how you think about that. A lot of times pre-launch, we're going to take a more conservative approach. We're going to hold on to some of that margin. We may choose to go make a design mod or something or change something rather than digging into that design margin because you're not on your way to orbit yet. Once you're in ascent or on your way to orbit, then it's a whole different ballgame. Now you're dealing with, you've already committed. And so that margin's there. It can help you It can help you mitigate other risks. If you do have an anomaly, it can help you mitigate other risks on orbit that you might choose to go do or want to go do to respond to that anomaly. And in this case, you can tap into that margin. Of course, you do the risk trade and communicate that with the entire community. And I guess my point here is, I say this from the standpoint of incorporating design margin for a 30-year used vehicle, but I think for the new exploration programs, they're not a 30-year reusable spacecraft, but the complexity and the extended duration, the remoteness of these missions, I think really begs for margin. So I think we really need to be concerned about that. Okay, that was the first one. The second one is understanding the physics of really everything we do through testing and analysis. This is really what engineering is all about. And this is our responsibility as engineers to do this, to understand this, and to bring this to the program and to bring this to the operations community so that we know what we have and we know what we're doing. Testing has got to be the hugest part of this. I'm a very much a test type person. We need to test to understand. If you don't have an understanding, go do some testing and get some data. But analysis is such a key part of that as well, because you can't always test everything you need to test, and you can't test the entire envelope. You need to have a way to explore other regions of the envelope, and analysis goes hand in hand with testing to help you do that. And in some of the examples that Jim was talking about, with the electrical connector and the testing we had to do there, and and I'm not talking about any specific kind of analysis, thermal analysis, structural analysis, GN&C type analysis, all of these things, I think the same thing is true. But like for that example on the connector, we had to do testing to kind of get a glimpse of that physics, but then we also had to do the analysis of the thermal response through that system to sort of validate the physics as well. They went hand in hand to get to that answer and to get to that resolution. So to me, that's just very important. Test and analyze things to understand the physics. Development testing early in a program can just provide tremendous benefit to the programs. Just a firm believer in this based on my experience in my earlier years and through Space Station. Space Station, they ended up cutting out a number of development tests that that some of us felt were pretty key because of cost, overruns and things like that. But I think they provide such a benefit and get you so far ahead in understanding what you need to understand that they're really worth doing. They validate sensitivities, they help you understand sensitivities and validate key assumptions in your analytical models. And then when you get to the flight hardware certification part, that has to be, I think, also based on a well-balanced set of qualification tests, again, and an analysis or detailed analyses. But they absolutely need to be, the analyses that you're going to use absolutely need to be anchored to the testing. Another thing I learned is testing at the various levels of subassembly. My example here is the docking system that I said I worked on for a number of years with the Russians. And actually, it was kind of interesting because the Russians didn't really have a very good modeling capability. They just didn't have the analytical tools and the computing capability to do what we were able to do here. But we started building docking system models and worked with the Russians with their testing capability. So we used basically, we took their docking system, very complicated. It's got hundreds of moving parts in it. It's like a Swiss watch, but it's kind of on a bigger scale. And we would take it apart and test all the different internal components, and then we built up a large, high-fidelity, dynamic docking simulation model, very detailed, that could really represent exactly what was going on. And so when we were testing in Russia, spent a number of months over there, we would be able to use this analytical tool, and when we'd have a problem in the testing, we could tweak things in the analysis, different components, and make it work a certain way, and we could actually predict exactly what failed on the hardware. And then we would, kind of open it up and show it to the Russians, and whoa, so they became firm believers in that analytical approach, that they really do go hand in hand. But you start at the building block level, build it up into the higher level system modeling, and then you really have to validate it at the system level. There's also the flight hardware acceptance testing, and that needs to be used, obviously, before you fly to validate key system requirements, performance requirements, and make sure it's acting the way it is. I mean, that's what we do at KSC. I call it acceptance testing, but it's also just the ground turnaround testing that we do at KSC to make sure the hardware is doing what we think it needs to do. And you heard this earlier, test as you fly as you test. That's the philosophy we need to have. There are limitations. We can't always, we're in 1G environment here, we can't always simulate that, but that's something we need to strive for and do as best we can. And I mentioned this earlier, but off-nominal testing and looking at malfunction testing to understand degraded capabilities and consequences of failure modes. This isn't always, I'll say, funded in the programs, but it's so important. We did so much of this with the docking system. We've done this with other systems. We tend to do this when we run into problems, then we go test it later and try to understand what the failure modes might be. But we learn so much from that. You really understand the full envelope and the degraded capability of your systems, and I think that provides a much more safer and reliable mission for us if we do that. So that's my testing and analysis.
All right, we need to
pick up the pace. All right. Continuous improvement. I got a lot of words here. I'll just say that, and you've heard with all the different elements talking, orbiter yesterday and the propulsion elements talking through, we need to stay hungry. We need to question things. We need to listen to the hardware. We need to believe the hardware. From an engineering standpoint, the engineers need to get the data. We need to bring the data to the table to help make these decisions. I think a program has to have a robust closed-loop post-flight and in-flight assessment process. The shuttle has a very robust one, I believe, right now. I think it's probably evolved over the years. I don't know how it was early in the program, but we need to do that. You need to have a way to look at all the anomalies that you might have in flight and understand them at what level they are. Do they need to come to the program? And then you need to have a mature enough and a robust enough process to work through all of those issues that you might identify and decide, do you have flight rationale? Is it just based on engineering judgment, as Brian O'Connor was talking yesterday, or is it really anchored into physics? And you can decide to fly as is with the program and the TAs, the tech authorities' concurrence on that, with that kind of communication and discussion. But don't be afraid to make modifications to the hardware if necessary. We've done that. Jim talked about a whole bunch of them. You heard in all the other projects about a number of modifications that have been made, even since Columbia, to do that. So the key lesson here is, relentless, continuous, or curiosity and continuous improvement of hardware and software. I didn't mention software, but we have continued to make software upgrades and improvements over the years. And that has, I think, over the last 30 years, has significantly increased our safety, reliability, and operability of the space shuttle. So that's the lesson learned. The last one is the team and the organization. Thanks, Jim, for keeping me honest here. And this, I think everybody summarized this. Maybe I don't need to go through it in detail, but I feel like this team which is just, it's thousands of people really. We're hitting on all 8 cylinders right now, and these are some of the things I just wrote down that I think are just so important and are a part of why we're doing so well. Leadership has this excellent communication skills, needs to, and I think does. Listening, talking, writing, all of those kinds of things that the leadership does so well, and really the whole team. The leadership is able to make the tough decisions and always communicate the reasoning. It's so important to get back to the team, the workers, so they understand what the decision was and really what's the rationale behind it. They may not totally agree with it, but I think this team does that. I think our leadership really communicates well. Embraces the entire team. We heard about alternate and dissenting opinions. The leadership embraces that and respectively seeks that kind of discussion. Individuals with integrity that understand the responsibility to speak up. You heard about that. I'm an engineer, so I put a lot of words here. Strong engineering team that is innovative, creative, curious, and that demonstrates engineering process rigor. We need to stay rigorous with what we do. We can't take shortcuts in our analysis and testing. We need to really work hard at that. And then the leadership that really expects nothing less, and I think we have that. Strong systems engineering. This is such a key aspect of what we do because some of the smaller individual problems are easy. It's when you get them into the big system and the interactions. The docking system by itself it's complicated, but when you get it in the vehicle and you got the crew doing the flying the vehicle and you got the GNC, things working, systems integration is such a huge aspect of that. Strong safety and mission assurance, a highly motivated team with passion for space exploration. Another key point, the NASA contractor team that works hand in hand. I think we have a great working relation with our contractors, and we really work in a badgeless environment. I think the diversity of the team, when I was in the NESC, I learned that there is so much capability across the agency and out in industry and in a contractor that it just provides great breadth, and it makes the whole team so much stronger. The governance model, you've heard several people talk about that. The program, the Engineering Tech Authority, and the Safety Tech Authority having that balanced authority to make these decisions. And I think that's made us very strong and safe. Independent assessment, heard Ralph talking about that, the healthy tension, an independent assessment of high risk for the checks and balances there. And then, of course, last but not least, the mission operations team and the flight crew that execute these missions. Of course, we're all part of that, but they really pull it off at the end there. So those are my lessons. I'll pass it on.
All right, thanks. John, Bob,
Okay, thank you.
you have 30 seconds.
Okay. Well, actually,
Wait, you're supposed to wait till the ground ops piece, and then you say you get 30 seconds, right?
actually, I can actually make this pretty quick because a lot of what I've got in my charts have really been covered, so I won't dwell on them. But let me just give you a little bit of background. In the United Space Alliance, several years ago, we created in our engineering environment, using our senior engineers, a knowledge capture. We always talked about the loss of corporate knowledge as people were leaving, and we thought it's pretty important to try to capture that knowledge, and that's evolved over the last couple of years into a more succinct lessons learned program. So we have been working with NASA and on this lessons learned program. So we had within USA, what we did, we had a gathering of all our senior engineers throughout the company, our chief engineers and engineering directors, and we collected somewhere over 200 individual lessons learned, those that were, they were involved in, that were important to them in their particular discipline. So what we've done, what we did, we took those 200 plus and categorized them, and this is what the list of categories that I've got here. Culture, starting from the top, because some of the things we talked about were in fact almost at the agency level, certainly program level. Management, integration, which you've heard a lot about here just from John and Jim. Design and operations, and like Ginger said in her opening remarks, United Space Alliance is primarily an operations company. So this collection of lessons learned has more emphasis on the operational, or operations, not operational, than design and analysis. So what I'll do is a couple examples, and I'll try to hit the highlight ones. And you heard this, Jan just said it over and over, and so important. Communication is so important. One of the things we did, and that's communication at the agency level among the centers. That has to be emphasized and made sure that proper communication among the centers, between the centers, is as it should be and open. And also in any program, communication between the elements. One of the things that we did, John McMahan and I today co-chair a shuttle program, NASA Contractor Chief Engineer Council, and it's a tremendous communication forum for talking any technical, not necessarily just technical, but any issue that we think is important. Somebody mentioned yesterday that we get into flight readiness reviews, and often we hear something that we don't necessarily agree with, but that's a forum where most of us are reluctant to stand up and say, I don't necessarily agree with that. And our Chief Engineer Council, we know each other well. We work together over a long period of time. We can duke it out and just share our concerns and challenge each other, and it's a tremendous forum. That's like John said, it's really a badgeless function, and it's a tremendous forum. John also talked about maximizing design margins, and I'll try to make this real brief. We talked from a cultural standpoint. You heard yesterday morning, Bob Thompson talked about the original shuttle design was going to be a 10-year program, and every orbiter is going to fly 100 missions. And I think the requirement was 240 hours ground turnaround, things that we knew were ridiculous, but those were the requirements. Obviously, we've flown now for 30 years. And there were a lot of things from a design standpoint that had to be looked at to go from a design goal of 10 to 30 years. So that you can't tell the future. Obviously, you can't predict the future, but if you can look ahead and anticipate how things may evolve, adding that extra margin, as John said, is really, really important. Another example of that we also heard yesterday was the International Space Station. We finally evolved to a station based on a Russian orbit. So we flew an inclination of 51 degrees rather than our nominal 20-some. But that drove significant changes, primarily from a weight reduction standpoint. Again, you can't tell the future, but anytime you can think about the way things might evolve and put that margin in, because we spent a lot of the Jim and the ET guys can tell you all about going to a super lightweight tank and taking out, in fact, I think you heard it yesterday, X number of pounds was a tremendous challenge based on a cultural decision at the agency level. Maintaining a open dialogue, dissenting opinion, you also heard that. One point I want to make about that, I won't repeat what you've heard, but to me it's very important. Dissenting opinions are crucial. We have to encourage people to speak up, as Jan said. But we also have to keep in mind, not all dissenting opinions are equal, and not all dissenting opinions deserve the same kind of attention as the baseline concept. You heard it when in God we trust, all else bring data. If you have a dissenting opinion, make sure you back it up with some factual data, something to support it, not just hand-wringing and the sky is falling. But dissenting opinions have got to be encouraged. It's very important. One of the other things that's really key to this whole panel is establishing a lessons learned program. We were late in doing it, I think, in our shuttle program, but it needs to be a program that's thought of in the very beginning, and it's because lessons learned program is really a three-step function. You got to gather the data. You have to have people to be conscious of a lesson that needs to be shared. And so you have to have a system of collecting that data. Then you have to have a system of when you want to go find out something, you can, like a keyword search, a search engine, something that will lead you. You don't necessarily know the right question to ask, but you want to go out there and see if you're in a design phase or a study, you want to go see if there's anything out there that may be significant to you. So you have to have a method of doing that. But then the real key is, how do you get people to know and to go look? I'll tell you, I was guilty back in the early Apollo days. We're the new guys on the block. We know how to do this. How stupid could we be? We did not want to listen to the people who have been through this. And so we have to make sure we have a program that encourages folks to go look, to go find out what's there. Actually, a good example, Jim mentioned the engine cutoff sensors. We found out after all that was said and done, after all the fixes that Jim just described, that had been learned, that lesson had been learned back in prior programs, unmanned programs, but the same exact failure and the same exact configuration and the same fix. And we did not know to go look for that. So lessons learned is so important. Otherwise, they're, quote, lessons experienced. The next category is management. I'm sorry, Mike Moses stepped out because the first one I have on my list is one that to me is very important, is decision making at the appropriate level. I think that the management textbooks call it the lowest practical level, but it really is important. Give you a little bit of a boring story. Back in the Apollo days, I worked on lunar module, and we were doing a late night, middle of the night test. A young guy, I got to work third shift. We failed a cabin fan. So in the middle of the night, we troubleshot that fan, excuse me, to make sure it wasn't something else causing it. We confirmed, in fact, we had a fan failure. We checked logistics. We had a spare. We removed, replaced it, reset it, because it was a very intricate installation based on for mass balance purposes, as you can imagine from a rotary equipment, and did a complete retest. And when the management came in the morning, we told them what we did. We gave them a status. Seriously, that can't happen today. That doesn't happen in today's culture. And I'm not saying that we need to go back to the way us third shift, young engineers just take off and do things, but also we need to, I think, back off from every decision having to go to program management. There's something in between that really makes sense, I think is really appropriate. And if Mike hears about this, I'm sure he'll catch me in the hall. You also heard this, test to failure is a very important program. You understand margins. If you test hardware to failure and you know, if you have a certain condition, you have a feel for how much more margin you have. Again, mentioned periodically review your certification. In fact, the example that I've got is one that Jim Owen just talked about, or John did, I guess, the main engine overpressure acoustic environment. In the last several missions, we were still doing gathering environmental data, the data from the acoustics and overpressure situation the main engine ignition caused, and then so that the orbiter and the other elements could go evaluate their capability of withstanding that environment. Again, this is very late in the program, so it's something you got to keep in mind from the very beginning. Another one that's very important from a management standpoint is requirement creep. I think somebody already mentioned that. It happens. Every problem, every failure we have results in changes in requirements, and a lot of them are very necessary, but some of them are maybe not quite so necessary. What I like to argue with some folks is we need to make sure that changes are mandatory. Not all changes are mandatory, and a quote that I wish I was the one that had come up with is something I think is very important to keep in mind. Often, often better can be the enemy of good enough, and just leave it at that. Transition operations, we heard that. I'm like Bob Thompson. I don't think we ever became operational in Shuttle, in Shuttle, but there was a time when somebody said after 5 flights you're operational. If you do want to, if there's a need to become, quote, operational, that decision needs to be based on technical and performance criteria, pre-established. Integration, as you've also heard, is very, very important. Early in the program, a lot of us were involved in our own specific disciplines, our own little areas, and didn't want to be bothered with worrying about other people. Well, it took me a little while to understand the significance and the importance of a strong systems engineering and integration function where you have to look at how one system might affect another one or one element might affect another one, and it's absolutely crucial. That within NASA in the shuttle program, that has been enhanced as a result of Columbia, and it's an incredible lesson learned. Don't wait till a significant failure. Put that in your program right up front. You heard about also flight instrumentation, the need for flight instrumentation. In the design review days, when I was part of that in the early shuttle days, a lot of us systems engineers wanted obviously more instrumentation. It's the engineer's key. You have to have data, but because of cost and weight concerns on the shuttle design, a lot of what we engineers wanted were deferred, or not deferred, but declined. And if you can overcome that, you pay up front, it'll pay for itself in the long run, as others have already mentioned. Also, something that was touched on, requirements should be documented as to why I'm doing this. And this is not a joke. After 30 years, there are folks that have said, why are we doing this? This doesn't make sense. But if you document the rationale up front, people, young folks come in, or people like me that are old and forgetful, we can go back and get a good understanding of why we're doing what we're doing. One of the things that is not on the chart, but we've learned late in the program, we wish we still had some of what I'm calling the integrated test beds. You saw a chart yesterday from Chris Singer where he talked about early before we flew the first mission, we had a main propulsion test article program at Stennis with the entire 3-engine set, orbiter main propulsion system, tremendous test capability, and we learned so much from that. And oh, by the way, late in the program, we wish we still had that test setup available. Granted, it would have been very cost prohibitive to do that, but it would have been great to have that with some of the issues that we worked late in the program. Another one that no longer exists would have been good to have late in the program was called a flight control hydraulic system lab that was set up in Downey, California, where we actually developed the flight control with hydraulic capabilities, and we helped design the hydraulic system. We called it FICL, of course. You got to have an acronym. But even late in the program, we were learning things in the flight control world where that would have been a tremendous capability. SAIL, the Shuttle Avionics Lab, still exists, and it's a very important integrated test set from an avionics to flight software testing standpoint that we use to this day. So, very important. Design, one of the most important points that I want to make from an operations standpoint is design your flight hardware to be maintained. And I'll tell you right now, the orbiter, because of cost and weight considerations, the orbiter design did not properly, in my opinion, accommodate maintainability. It's just a fact. It was driven there for reasons that were important at the time. But if you go in today to go replace a significant black box or piece of hardware, and it's hard to get to, in some cases you have to remove other hardware to get to it, the chances of potential collateral damage is extremely high, and keep maintainability in mind in any flight hardware design. We already talked a little bit about when you're designing and trying to understand environments, you got to look at the big picture. I'll give you a quick example. The external tank doors, the doors that close after orbiter ET separation, that isolate the feed lines from the tank to the orbiter and the power system from the tank to the orbiter. Those doors, of course, have to close. That's on the belly of the orbiter. We call them ET doors. Those were designed, the mechanism was designed taking into account a certain amount of ground test and one flight cycle. Well, nobody thought about what it was going to take, how many times we had to cycle those doors for TPS, thermal protection system work, because they're all covered with the black tile. And when the doors are open, there's a place to install the jacks in the OPF. And there's another location, but we cycled those doors many times more than they were ever designed to be cycled. We found a crack at the pad one time. I forget which mission, it doesn't matter. In part of the linkage, we had to roll back, beef up the linkage, go back to the pad, and all because, seriously, we did not anticipate the total number of cycles that door was going to receive because of ground operation considerations. Same thing, I won't go into it with the main landing gear. It was designed, the mechanism was designed for a certain number of cycles based on flight and ground test, but we cycled the doors many, many times, primarily for thermal protection system considerations. Let's see. One of the things that to keep in mind in design is designs are requirements are based on new builds, new build design. We wind up with, if you do have reusable hardware, and hopefully we'll have reusable hardware to be reflown again, you need to keep in mind that there are certain requirements that apply to brand new design off the assembly room floor, so to speak, as opposed to something that's flown several times. In the Apollo, in the shuttle program, we created what we call a fair wear and tear spec, and it's very important. And I'll go to my last chart. Operations, and again, this is primarily from a, thanks, Steve, primarily from a ground operations standpoint. Requirements, the ground operations requirements should never be more restrictive and than the component acceptance test and the original design certification test. And often we've had people try to impose requirements, test requirements that were more stringent than the original design requirements. Risk assessments you've heard about, electronic wide generation, you guys are way ahead of the curve on that one. Don't need to mention that one. Calibration of tools is important, and let me just wrap up with going back and repeating something I said about lessons learned. We want to make sure, you really want to make sure that lessons are learned and not just experienced. The key is to make sure that you have some forcing function to make folks go and look at what those are. You don't know what the right questions to ask, but you need to enforce, like in the design review, have a lessons learned search somewhere in the design review checklist as an example. And that's all I have. Thank you.
All right, thanks, Bob. Steve, bring us home here.
All right, bring it home. How much time do I have? 2 minutes, okay. So that's the first lesson in ground operations. Flight design always takes too long. Right? All right, so I'm going to go through these. I wanted to leave you with a couple of thoughts. I know a lot of you guys want to be propulsion designers. This is what it takes to change out a signal conditioner card on an ohms pod. So whoever designed this propulsion system, I mean, they might have been taught in school operations and sustainability. To actually physically go change it out, you have to go and find a technician that's about 6'3" with a certain reach and length. There's a Teflon sheet of material there. And then when the technician actually reaches forward into the shuttle to change out the card, somebody actually holds his feet so we don't lose them down into that hole. So if you take away one chart, it's sustainability. It's the difference between having your vehicle in the hangar or having it flying. So next chart is if you have an inspection call out, this is a technician inspecting a block on top of the lightning mast. Everything that you specify in requirements has a consequence. So we have to send somebody up on top of the lightning mast and go inspect the rod after strikes or for corrosion damage. So one thing the shuttle program did very good on is that every problem that we had an applied physics group, another group of people, and then whenever we stumbled into problems, they would look for innovative ways to try to solve the problems. And then some of these innovative ways actually made themselves into spin-offs. This is a fail-safe jack screw. Jack screws are used everywhere in every application, flight and ground ops. There's 4,000 of them in ground operations. The Cox vent hood actually broke off or actually got damaged during one of the lift operations. They started studying it. They came with a very innovative way that you can put a follower nut behind the jack screw, and you can actually measure the gap between the follow nut and the primary nut, and you can actually see that the components start failing. And if you lost the primary side, the load would be taken up. For a very simple fix, you can actually have a fail-safe jack screw that can cause no problems. I'm going to crank through a lot of these really fast. So this is an ice detection camera system. You can set it on the deck of the mobile launch platform, shoot it towards the tank, measure the density and thickness of the ice. It's being used with TARDEC up in measuring icing on aircraft, and it's a spin-off that I think you'll see in the future. Very portable. Another one's hail monitoring systems. This is deployed in a lot of airports right now. One of the way we got hit by several times in the program on hail, how to measure how big the pellets are, the density of the ice. This is an acoustic device, worked with Colorado State University, developed hail monitoring systems, and it's actually deployed across the U.S. This looks like a real simple device. It's back from the 70s and 80s. It's used on every crime scene that you see in the United States. 2 little laser dots you put in the photo. It's actually marketed by several manufacturers now, or a cube that actually, so when you go back and look at photos, you can recreate the data engineering-wise on what it is. Laser leveling systems, these are early. Roundness of the solid rocket booster. Tools were invented for circularity of the solid rocket booster components. A pendant for controlling the hydrosets as you move this heavy equipment around. NASA worked with Del Mar Avionics to develop a wireless pendant that you could walk around. You see these in industry all over the place. A lot of fail-safe capability into this component was developed. Laser alignment tools, acoustic measuring tools, image analysis tools used for recreating ascent trajectory analysis. This one's interesting. You can take any 3 views on the pad and look for birds. Kind of an unusual thing, but you can actually track in X, Y, Z coordinates from any 3 photo images or video images in real time. Track any bird that's flying out there prior to launch. Actually hit a bird a few launches ago. I almost went through the window inspection. Every flight we see micrometeorites hit the windows. This is a non-invasive way of inspecting the window for damage and trying to characterize the damage in depth. It actually mounts on the window by suction cups. Laser scans the image, and you get a very accurate depth of the glass and the damage. Water inspection, the tiles sucked in the water. I'm sure in the previous lectures we talked about how much you can take a gallon of water and pour it into one tile. So the amount of water absorption into the tile, you can see this is a picture of kind of milking the water out of the tile post-flight when it got rained on, probably from delivery. We have water detection guns now that monitor how much water is in the tile. That's being used for some other applications. Aerogel, everybody studies in school, but it's already in use out in the pad today for our ground umbilicals. Acoustic measurement leak detectors. Actually, you can actually hear the leak with this acoustic device. Fire detection systems. This is a tape that they've invented. They've only put this on the pad a few times, but if this tape is exposed to a gas, it can be exposed to hydrogen. You can make it monomethylhydrazine. But it'll actually turn colors. So if you're trying to find a leak, it's very handy. You can see how it's starting to turn brown. So as it gets exposed to different chemicals, so they're looking at on different tapes that are for chemical exposure. Green lubricants, we have green lubricants that were developed as part of our processing. Things that we have to use a lot of that might actually get put into the soil. Develop green lubricants, we'll skip that one. This is a self-diagnosing cable wire system. This is deployed especially on military type systems, but you could string in 15 different types of cable, speaker cable, shielded twisted pair, anything, you can string it together. You teach it what it looks like, and then if you have a fault, it'll actually tell you the fault down to about an inch or so. So if you're trying to diagnose a problem, it's very handy. It's marketed through Eclipse. Another one is self-healing wire. If you nick this wire, it was invented by the same person who invented self-heating MREs, the meals that heat up when you pull the strip back. So if you nick this wire, these little microcapsules flow in around it, and it will repeal. That actually had add color in it because you could not tell the difference between where the repair was and where the original damage site is. But these are all spin-offs that came from ground processing. And then tile maps, extensive use of tile on this space shuttle, mapping the damage, mapping the repairs. Everything's internet-based now. And then the final thing I want to close up, and I think somebody mentioned it earlier, but there is a book out now by the Shuttle program. It was took 3 years to produce, but it's a broad systems engineering approach of everything that the Space Shuttle program learned, and it has examples on it. It's $42, I think, on Amazon, but they can go through, physiology on the astronauts, colon cancer research. They talk about flight structures. They talk about integrated systems. They'll mention that on the body flap on the first flight actually went to full deploy. So, and things that they didn't think of in the original design, that these are kind of lessons learned. This book was written by, I think, about 330 engineers. So you have to take it in small doses when you read through. It's not one you start from cover to cover. But every time you pick it up, you can pick up a lot of lessons. And if you took one thing away, it's how to build an integrated system across structures, electrical, because we all tend to kind of migrate to our discipline and not really worry about the electrical guys or the mechanical and that. So this book's available, and that's my pitch in 5 minutes or less. So, all right, okay.
So I did a horrible job, and I ate up your question times by not controlling these guys. But what I would suggest is that you grab any one of us and ask us questions offline, and we'll be glad to answer them. And again, you can tell the way they talk about their particular part of the program, the passion that they have for space flight, human space flight. And we really appreciate the opportunity to talk to all of you, and we're glad to answer any of your questions offline. So Ginger, I think we're at time for lunch. Is that? And lunch is in the ballroom. So thanks again.